Okay, I think it's 10 and we should get started. What happened here? Let's see, maybe the connection didn't work out. Okay, so you can see my screen, right?
Yeah, we can.
Okay. So morning, everyone. This class, we're gonna introduce some new topics here. So we're gonna talk about the VOC incinerators, but if we just briefly go through the contents of last class, so we gave an overview, a very brief overview about the method we can use to remove the VOCs. So basically, I think it's a class before the last class. We talk about how we can use the vapor pressure to remove the VOCs. We can just reduce the temperature of the system, right, to let it condense, and then we can remove the VOCs. So someone's sending me a chat that are we supposed to be seeing a PowerPoint? I think right now you should be seeing the PowerPoint, right? Or are you seeing another screen? Yeah, just let me know if you can't see the slides, all right? I can make some adjustment here.
Yeah, I don't think we're seeing the slides. I think we're seeing a different screen.
Let me reshare my screen. Okay, so what about now? You're supposed to see a slide with the recap on it. Can you see that?
I think we're seeing like a document about like a VOC incinerator, some kind of problem.
Let me stop share and then go back. Okay, so what about now?
Yeah, perfect.
The recap, okay. Yeah, so this is basically what we learned from our last class. So we talked that we can reduce the temperature to remove the VOCs, basically condense them into liquid, right? And then collect these VOCs. We can use absorption. So absorption means some VOCs can get penetrated to the inside of the liquid, right? We can use this method to remove the sulfur dioxide, actually use the absorption by exposing these gas species to the liquid. We can also use adsorption. So adsorption means the gas molecules can just get adhered to the surface of the solid. We mentioned that we can use the activated carbon. The activated carbon to remove the VOCs. So we also mentioned about the chemical reactions. We basically went through some general concepts about the reaction rates and also the, let's say the rate constants, the chemical equilibrium and so on, right? So in terms of the chemical reactions, we can directly use the combustion method, which is the VOC incineration, and also the catalytic reaction, which basically reduce this temperature of the reaction. And then we can achieve a more complete reaction of this system, right? And so this class, we're just going to talk about this method, which is combustion method, or the VOC incineration. So I think right now you guys should probably be quite familiar with this reaction now, which is the hydrocarbon reacting with oxygen. And we also write out the nitrogen here. Basically, the hydrocarbon will get oxidized to form carbon dioxide and also the water here. Okay, so I mentioned that we should use this type of reactions when we deal with the coal combustion, when we design the coal-fired power plant, mainly because whenever we introduce the air into the combustion, we're always sending in nitrogen here, right? So if I just give a very quick quiz, So why do we need to add 3.76 in front of the, or in the nitrogen for this reaction here? Okay, 10 more seconds. All right, I think we can stop here. So it is because there is nitrogen in the atmosphere, right? We mentioned that whenever we combust the fossil fuels, we're always sending in the atmospheric air, right? So in there, there's always nitrogen. And the reason why we always want to put nitrogen here is to consider how it might affect the volume of the reaction, because there's always some nitrogen that are not being reacted. So they're not participating in the reactions, but just changing, let's say, the flow rate into the combustor, and also the flue gas flow rate, right? So that's why when we, let's say, when we design the pre-cleaner or the cyclones or the ESP, when we calculate the volumetric flow rate, we need to consider the nitrogen that's being introduced into the system, right? So one thing that also quite interesting is that I'm not sure if you actually considered how this 3.76 come out, okay? So I mentioned that it is related to the composition of the air in the atmosphere. So if you check the composition, that's actually 78.09% of nitrogen, and then 20.96% of oxygen. If you add these together, you can see that it's somewhere around 99%, right? So there are some remaining gas species, for example, argon, right? And then there are carbon dioxide and so on, so forth, okay? So these will occupy around 0.95%. So these gas species are also inert. They're not participating in any reactions here. So if you look at this 3.76 number here, so if you do a calculation, I think we can just demonstrate. Do a calculation. If you directly use the ratio between 78 and 20.96, it is not 3.76, it is 3.72, 3.73, right? So basically this number here is not exactly the ratio between nitrogen and oxygen. It is actually the ratio between all of the rest of the gas over oxygen, right? So I think this is 79.04, right? So the remaining gas occupies around 79% of all the gas, right? And this is around 3.76. I think there are something, probably some approximation here, but for this 3.76 value here, it is considering all the gas species that are not oxygen. So theoretically, we should not put nitrogen here. We should put nitrogen, argon, carbon dioxide, and so on. Okay, but they don't change the number here. They don't change what is the flow rate that we send into the reaction, or what is the flue gas flow rate, because all of these gas species, they're not participating in the reaction. Okay. So this is the general formula for the reaction of any hydrocarbon here. And we know that for the reaction, if we want this reaction to be stoichiometric, then we need to consider the situation where all the carbon is converted into carbon dioxide, and then hydrogen is converted into water, right? So based on the chemical formula, we can calculate what is the B value here under the stoichiometry. So we know that there's a 1-to-1 ratio between the carbon and the oxygen molecule, right? So that's why if we want to calculate B, that's X, because X amount of carbon is going to get converted into X amount of carbon dioxide. And then in terms of water, then that's going to be Y divided by 4, mainly because 4 hydrogen atoms will react with 1 molecule of oxygen to form 2 molecules of water, right? So that's why we have Y divided by 4 to be the number that's corresponding to the hydrogen, okay? So this B value here is the stoichiometric number of moles of oxygen required per mole of the hydrocarbon. And this 3.76 is the number of moles of nitrogen present in the air for every mole of oxygen. So we mentioned that strictly speaking, this is not nitrogen. This should be inert gas. Okay, it's just nitrogen is occupying most of the contents there. But one thing we have to pay attention is that for this reaction here, although we write it out as a single reaction, but if you consider the details of the reaction, this is never a single step reaction. Okay, so we mentioned that in order to let a reaction to take place, it is basically the bombardment of all the molecules, right? For example, this one is an oxygen molecule, this one is a hydrocarbon, right? So we have to let the oxygen molecules to collide with the hydrocarbon molecule so that we can have enough energy. And this energy also have to be higher than the activation energy. So basically, this bombardment energy, let's say the kinetic energy, has to be higher than the activation energy in order to let the reaction to take place. But if you look at this reaction here, it's going to need multiple number of oxygen, right? So if this reaction is a single step reaction, what that means is this B number of oxygen molecules have to collide with the hydrocarbon all at the same time, which is a very low probability thing. So this is never going to happen because the gas species is so dilute. There's never a coincidence that all of these molecules can collide at the same time. And therefore, this reaction is never a single step, right? So we have to separate into multiple single step reactions. Okay, so it's not going to happen right away. And that's why we will introduce the concept of the chain reactions. So basically the chain reactions is separating a global reaction. We can call this as a global reaction. Separating this global reaction into multiple steps, say separating 1, 2, 3, all the way to the end. All the way to the end, where we can form carbon dioxide and water. Okay, so each step can be happening at a single step, right? Each reaction is a single step. So we can let these hydrocarbon to be oxidized. So actually this chain reaction is very, very complex. Even for the most simple hydrocarbon, let's say methane, it is composed of multiple chain reactions. And here I'm just listing a few of the reactions, a few of the chain reactions for the methane. And actually, people spend a lot of efforts in understanding the reaction of methane, mainly because it's the major component of the natural gas, right? To boost up the efficiency for the fossil fuel combustion, we need to know what is happening in there. And up until now, I think people have already discovered more than 100 chain reactions. okay? So even for the most simple hydrocarbon, its reaction is going to contain a lot of steps. And here I'm just listing all the representative steps. So for example, the chain reaction have to have a chain initiation. So the initiation process is basically the methane colliding with an oxygen molecule to form an CH3 radical and a hydroperoxide radical. So this is called hydroperoxide radical. Hydroperoxyl radical. Okay. And then these hydroperoxyl radical, HO2, actually can react with some species. For example, here, right? It's forming more complex radicals, right? And then further decompose these hydrocarbons. And also, I think for the reaction of the methane, the existence of the hydroxyl radical is also very important. So this is called hydroxyl radical. So you can see that the hydroxyl radical is basically formed by an oxygen molecule colliding with a CH3 molecule. Okay, so we can generate a hydroxyl radical, and the hydroxyl radical is very strong oxidant. Okay, so the hydroxyl radicals can further decompose these hydrocarbons to form water, and then also to form the let's say to form the carbon monoxide. Okay, so basically it's the formation of the OH and HO2 radicals that are oxidizing the hydrocarbon. Okay, so you can see that even for the reaction of the methane, this reaction can be very, very complex here. So this is a major difference between the global reactions that we mentioned here and the chain reactions. So due to the complexity of this series of reactions, people actually find something that's in the middle. You can think of it as a compromise when we're trying to understand the combustion of the hydrocarbons. So the way people use is actually to consider a scenario where the hydrocarbons reacting with oxygen to first form carbon monoxide and water. And then the carbon monoxide can get oxidized further to form the carbon dioxide. Okay, so we're summarizing a few reactions here. Let's say you can indeed see that for the methane reaction, the carbon monoxide is one of the component that's being produced from this set of reactions, right? And then after the carbon monoxide, which is relatively stable compared to all the other radicals, this carbon monoxide can further get oxidized by oxygen to form the carbon dioxide. So we're basically separating the entire global reaction into two steps, right? And even for these two steps, they're not happening in the same step. We're just assuming that we can treat it as a single step reactions here. And since we make this assumption here, we can start to analyze what is the reaction rate for this oxidation of the hydrocarbon. Okay, so first, one thing we can do is we can add the numbers in front of these reactants or products here based on the stoichiometry, right? So again, you can see that based on the stoichiometry, then the number in front of the oxygen will be X plus Y divided by 4, right? And then it's going to form X number of the carbon monoxide. And since it's forming carbon monoxide, so here the number should be X divided by 2, right? So there's a 1-to-1 ratio between the carbon and the oxygen atoms. is forming X number of carbon monoxide and then Y/2 number of water. And then this X number of the carbon monoxide can further get oxidized by X/2 number of oxygen molecules to form X number of carbon dioxide. Okay, so we can assume certain reaction rates or the rate constants. Let's say the rate constant for the first reaction is K1 and the rate constant for the second reaction is K2. Okay, so if we make this assumption here, then we can calculate what is the reaction rate for all of the different species in here. So for example, if we're interested in the reaction rate of the hydrocarbon, then we can see that reaction rate of CXHY is going to be equal to minus K1 multiplied by the concentration of CXHY, and then the oxygen. Okay, because the reaction rate is dependent on the rate constant, the concentration of the hydrocarbon, and also the concentration of the oxygen. Okay, so we can also calculate what is the rate constant, what is the reaction rate of the carbon monoxide. So we know that the carbon monoxide is being formed in the first reaction. That's why we should use K1 CXHY multiplied by oxygen. And then we should also multiply an X in front of this reaction rate because there is an X in front of the carbon monoxide, right? And also we should notice that the carbon monoxide is being consumed by the second reaction. Basically, they're being removed due to the reaction, right? So we should add in this minus term here, which is K2 of the carbon monoxide and then the oxygen. Okay, so we can also write out the reaction rate for the carbon dioxide, which is basically K2, CO, and oxygen, right? We just consider what is the rate constant, which is K2, and what is the concentration of these reactants, okay? So these are the reaction rates for the reactants and also the products. But one thing we should pay attention is that for a lot of the VOC oxidation, we're going to put in sufficient air into the system, or much more air, okay? Which means that the oxygen concentration is going to be much, much larger than the hydrocarbon. And what this also means is that if we combust or if we consume the oxygen from the reaction, this consumption is going to put a minimal influence of the oxygen concentration. Okay? Since we put in so much large amount of oxygen, so even a small fraction is being consumed, the oxygen concentration was still treated as a constant value. So what this means is that we can simplify this reaction rates here. So we can just combine the oxygen into the K1 constant here, right? Since they're in large amount, their concentration is not being affected by the combustion, right? We can just combine these all into the rate constants, okay? And then we can simplify this set of reactions. So basically, we're going to have the reaction rate of hydrocarbon is equal to minus K1 CXHY. Reaction rate of carbon monoxide is X multiplied by K1 CXHY minus K2 of the carbon monoxide concentration. Okay, and then the formation rate of carbon dioxide is K2 multiplied by CO. So basically, we're just ignoring all of the oxygen concentrations. Okay, so by ignoring that, we can have this new set of reactions or this new set of equations. So if we further write out what it means for these different reaction rates, so you can see that the reaction rate of the hydrocarbon is actually just dCxHy dt. So this is how we define the reaction rates. Okay. For the reaction rate of carbon monoxide, that's dCO dt, and this is dCO2 dt. So one thing you can notice is that for this set of differential equations, we just have three unknowns, which is the concentration of hydrocarbon, concentration of carbon monoxide, and the concentration of carbon dioxide, right? So if you check all of these concentrations, there are just three unknowns. And we have three equations. So theoretically, we should be able to solve them with an analytical solution. Okay, so there is an analytical solution here. So if you have taken the calculus, I think this is a kind of typical problem that you are going to deal with. Okay, and because one thing we know for sure is that if you just look at this first reaction here, or this first equation here, so we have dCxHy dt equal to minus K1 multiplied by CxHy, right? It's just like dy dt equal to minus K1y, right? We know that for this type of differential equation, there is a solution that y is equal to y0 exponential of minus K1t, right? So this is a solution. And then if we know this solution here, we can just plug it into the second reaction and the third reaction, second equation and third equation to solve what is the concentration of the carbon monoxide and carbon dioxide, okay? So this is very similar to the problem that are shown in this graph here, okay? So in this graph, it's dealing with a reaction of A being converted into R, and then R being converted into S, okay? So you can think of A as the hydrocarbon, right? R is the carbon monoxide, and then S is the carbon dioxide, okay? So we know that the first reaction has a reaction rate of K1, second reaction has a rate of K2. So how does the concentration of the A and R and S change as a function of time? It is actually plotting the concentrations of all of these species, okay? So as we mentioned, this hydrocarbon concentration is going to decrease exponentially, okay? So that's why it's going to have a exponential decrease, and this is going to be for sure, okay? So this is the A species, or the hydrocarbon. Okay, it's always going to decrease, right? And then in terms of the R, it's going to take a shape that looks like this. It's going to first increase and then decrease. So basically, if you look at the reactions that we listed here, this indeed makes sense, mainly because for the species R, which is a carbon monoxide, it has to rely on the first reaction to form this carbon monoxide, right? And then once they're being formed, they can further get consumed by the second reaction, which is oxidation. And their concentration really depends on how fast is the K1 and how fast is the K2. Let's think of some extremes here. Let's say if the K1 is very large, so all the hydrocarbons are getting converted into carbon monoxide instantaneously, right? So then we're going to have a very high concentration of the carbon monoxide. But if the K2 is very slow, then this carbon monoxide will get, right? Although we know for sure that since there's limited amount of hydrocarbon, what that means is going to be limited amount of this means is that finally, I mean, at the, let's say, years or hundreds of years later, because these carbon monoxide are getting consumed by the second reaction, so their concentration will definitely decrease to 0, right? So that's why if we plot out the carbon monoxide concentration, they will first increase, right? First increase and then decrease. Okay. And this maximum amount really depends on how fast is K1 and K2. So we mentioned that if the K1 is infinitely larger than K2, which means that the carbon monoxide is getting carbon monoxide getting formed in a very fast way or getting accumulated in a very fast manner, right? Then we have basically K2 divided by K1 is very small. So K2 divided by K1. If the K1 is infinitely larger than K2, then this term will go to 0, right? So when it's, let's say, for example, if the value is close to 0.1, then they're going to go with this shape here. Well, if the K1 and K2 is equal to 1, which means that the K2 is getting larger, then that means the curve will be basically will grow shorter, right? So there's going to be less amount of carbon monoxide getting accumulated. But if the K2 is much larger than K1, which means that the second reaction is much faster than the first reaction, then we can't have any accumulation of the carbon monoxide. So that's why you can see the reaction rate of these two equations really determines how we accumulate the reactants in the system, right? And then in terms of the let's say the concentration of S, then we know for sure that the concentration of S will always increase, right? And this is because carbon dioxide is kind of like the terminal product in this reaction. Carbon monoxide is not going to get further oxidized, right? So that concentration is always going to increase. So basically, this is how you can tell what is the concentration. How does the concentration of these reactants or products change as a function of time here? Okay. So we talk about the reaction rates or the reaction kinetics, but in terms of the real application of these VOC combustion, there are some requirements. So there's a term called the capture efficiency and the destruction efficiency. Okay, so destruction efficiency means how much the hydrocarbon are getting destructed or getting combusted. Okay, so the capture efficiency means how efficient are these hydrocarbons getting collected. Okay, so these two efficiencies are not related to each other. So you can, for example, you can have a 100% collection efficiency, but you just have 10% of the combustion efficiency, right? Or you can have 10% of the collection efficiency, but have 100% of the combustion efficiency. So the overall removal efficiency will be the product of these two efficiencies. Okay, so here it's just going to it's just listing some criteria in terms of making sure that the capture efficiency is 100%. Okay, so for example, it asks that for the industries or the industrial processes that generate the VOC, we have to make sure that all openings, for example, doors, windows, must be less than 5% of the total enclosure surface area. So this is just to make sure that the air is not getting leaked to the outside environment, right? We also need to make sure that the air flowing inward have to have a phase velocity of certain values, have to be above that velocity. Otherwise, if the velocity is lower, then it's going to facilitate or make it easier for the air to leak outside. So all the sources emitting the VOCs inside the enclosure must be distant from any openings. This also makes sense, right? So let's say if we have a duct, and then we're forming VOCs inside, let's say as a point source here, it's forming VOC molecules. Okay, so we want to make sure that there are no openings just close to this source here. Otherwise, the VOCs will just get leaked outside, right? We want basically want this to be a closed system, right? So all the exhaust streams must be directed to the thermal oxidizer or other final control devices. So the thermal oxidizer is basically the process or the device that we remove these VOC by the combustion or incineration. So finally, all the windows or doors not counted is in the 5% area rule, right? So this is again regarding the regarding how do we design such a system that we can make sure that there is no air leakage, right? So in terms of the VOC control with this combustion method or the oxidation method, there are again two ways, right? We mentioned that there's direct combustion or incineration. So this is called the direct thermal oxidation. And we can also add catalyst to this process, which can generally allow us to operate the reaction at a lower temperature here. And here I have two short videos showing how these two processes work. Then we can take a look here.
Effective air pollution control systems are essential and required in today's industrial landscape. Organizations are obligated to keep their facility in compliance with current regulations and to continually seek opportunities to reduce their environment impact. Pollutants like VOCs, or volatile organic compounds, are emission issues that must be treated before being released to the Earth's atmosphere. And a common method to treat VOCs is the use of a thermal oxidizer. A thermal oxidizer can be likened to a burner in a box. By burning or heating up the VOCs to a certain set point temperature, they are oxidized. This oxidation process breaks down the harmful particulates into carbon dioxide and water. Thermal oxidizers work well with applications where particulates may be present or have higher concentrations of VOCs. Also known as a fume incinerator, a thermal oxidizer, when designed properly, will treat a wide variety of process flow rates and VOC concentrations emitted from a facility. It all starts with the chamber, which houses the heating element to burn the VOCs. The chamber is heated to a set point temperature of approximately 1500 degrees Fahrenheit. Once the set point temperature is reached, the fumes are brought into the chamber through a system fan. All VOCs present are oxidized and are broken down into carbon dioxide and water vapor, which carry through the system and out the stack into the Earth's atmosphere. Thermal oxidizers are very effective, with a greater than 99% destruction rate. However, they are not as thermally efficient. A straight thermal oxidizer will lose all the heat energy employed during oxidation. However, there is a simple solution that modifies a straight thermal oxidizer and can make the system more energy efficient. By implementing a heat exchanger, existing heat can be captured or recuperated to be reused within the system. Recuperative thermal oxidizers are an alternative to straight thermal oxidation. Adding a heat exchanger allows the system to reuse energy, which helps reduce operating costs. By recovering the thermal energy within the system, operators can minimize the amount of auxiliary fuel needed for the burner, or can even fulfill additional heat energy requirements needed in other facility operations. Designing the right system for your application is key to ensure compliance with regulations and operating requirements. Understanding how the equipment will be used, loading requirements, permit requirements for removal efficiencies, and various other factors must be considered when designing a system. At Pollution Systems, we understand that every application and process is different, and we leverage our industry experience and expertise to apply the appropriate technology to each customer's air pollution control requirements.
Okay, so this is the video showing the design of a thermal oxidizer, right? So we can see that basically for the thermal oxidizer, it's just pure the combustion of the VOCs. And it did mention that some of these processes are not efficient, mainly because we're not using the heat. And this is also because when we combust the VOCs, we have to operate it at a very high temperature. So one method we can reduce the temperature for the operation is to add in catalyst, right? So that's why there's also a process called the catalytic oxidation. So I also have a short video showing this setup here.
Catalytic oxidizers are used across a broad range of industrial processes to efficiently destroy volatile organic compounds, VOCs, hazardous air pollutants, and other odorous emissions while enabling manufacturers to maintain EPA compliance. This proven technology combines a low-temperature oxidation catalyst, primary heat exchanger, and an efficient combustion system into an integrated package delivering cost-effective destruction of VOCs. Upon startup, the line burner is ignited, raising the temperature of the burner chamber to the set point required for catalyst activation. The system booster fan draws in the process emissions and forces these gases into the inlet of the heat exchanger. The heat exchanger preheats the incoming emissions by transferring energy from the hot, clean exhaust stream exiting the oxidizer. These gases pass through a high-efficiency line burner, where the temperature is raised to the required set point temperature ranging from 500 to 650 degrees. Depending on the process emissions, a guard bed may be added to the radiant zone in the burner chamber, where contaminants can be trapped, protecting the catalyst bed. The heated process emissions then enter the catalyst chamber and pass through the catalyst bed, where the VOC destruction efficiency is in excess of 99%. The catalytic oxidation reaction converts the VOCs into CO2, water vapor, and energy, causing the temperature to rise across the catalyst bed. The hot, clean exhaust stream passes through the counterflow heat exchanger, where BTUs are transferred to the incoming process emission stream. In most situations, the thermal efficiency of the primary heat exchanger can range from 60 to 75%. This level of thermal efficiency provides energy to preheat the incoming process emissions, minimizing fuel consumption from the burner system. At the exit of the heat exchanger, the clean, cooled exhaust stream is discharged to atmosphere. The catalytic oxidizer, one of many CPI air pollution control solutions. Catalytic Products International, enabling clean production since 19.
Okay, so you can see the major difference between these two systems, right? So they're using the same reactions. It's just the catalytic oxidations are using catalysts to reduce the temperature of the reactions there, so that you can have a higher efficiency and also higher thermal efficiency in the system. Okay, and then one thing we have to discuss is about what is the correct temperature? What is the optimal temperature to oxidize the VOCs? Okay, so if we're just talking about the direct thermal oxidation, we know that the catalytic oxidation generally has a lower temperature in terms of its operation, right? But unfortunately, I think most of the industrial plants are still using this direct thermal oxidation, okay? So because of that, we need to find out what is the optimal temperature to operate these oxidation processes. So there are several methods to calculate this oxidation temperature. For example, a most direct way, let's say the design temperature, is by using the Ross method, okay? So what the Ross method defines is that basically the direct thermal oxidation temperature is around 300 Fahrenheit higher than the auto ignition temperature. Okay? So there's a new concept here which is called auto ignition temperature. I think it explains what it means by the words here. So basically what that means is if we have a mixture of the VOC and oxygen and nitrogen, okay, basically with air, then if we raise up the temperature, we're going to hit a temperature where, let's say a critical temperature, where the VOCs are going to auto-ignite, right? So basically we're going to have the combustion. And what the Ross method defines is that the optimal direct thermal oxidation temperature should be around 300 Fahrenheit, higher than this auto-ignition temperature. Okay, so our textbook is showing the auto-ignition temperature of some selected organics or VOCs in the air. So these are all the auto-ignition temperatures. So if I just give you a quick quiz, can you help me find out what is thermal oxidation temperature of methane according to this method? Please pay attention that this is the thermal oxidation temperature, not the auto-ignition temperature, okay? Five more seconds. Okay, we'll stop here. All right, so it should be 1299, okay? So the way we deal with this problem is just to refer to this table. We can find out that methane is here, right? It has an auto-ignition temperature of 999, right? And then we need to add 300 Fahrenheit to this auto-ignition temperature to get the design temperature or the thermal oxidation temperature for the system, okay? So this is a Ross method, which is quite straightforward, right? But people also realize that this is, we all know that the most simple method might not be the most accurate method. So that's why people are also practicing with other methods to do more accurate calculations, okay? So the second method is called the Lee-Hansen method, okay? So this, actually this Hansen here, this is Dr. Ronald Hansen at Stanford University. So he spent a lot of efforts in understanding the combustion of a lot of the hydrocarbons. So actually he designed a laser diagnostic method to study how complete the hydrocarbons are getting combusted in reactors, okay? So they came up with this method to deal with the, or to find out what is the optimal oxidation temperature for the hydrocarbons. So it's composed of quite complex equations, but by just explaining how they're getting, what each term represents, you can see that this is also quite straightforward, okay? So there are two temperatures. One is T99.9 and the other is T99, okay? So the T99.9 means the temperature for a 99.9% destruction efficiency, while the T99 is for 99% destruction efficiency. So these are for different destruction efficiencies corresponding to which temperature we're interested in, okay? For example, if we're talking about the 99.9, okay? So it's calculated by these terms combined together. We have 594 minus some term, W1. So W1 means the number of carbon atoms in the system. So let's say we talk about the methane again, okay? If that's the case, then W1 is going to be equal to 1, okay? And we have W2, which is aromatic component flag. So there's no aromatic in the methane here, right? And W3 is the carbon-carbon double bond. So methane doesn't have carbon, doesn't have this double bond here, okay? W4 is a number of nitrogen atoms, so on and so forth. So for each term here, you can find out what is their meaning. So you can just refer to the chemical formula to fill in this parameter and calculate what is the temperature for this thermal oxidation. Okay, so there's an example problem for the for using this method, this Lee-Hansen method. Okay, so maybe we can briefly go through this question in our next class. Okay, so there are some interesting behaviors or interesting phenomena here. You can see basically what is determining whether there's a plus sign or negative sign. Okay, so we'll talk about that in our next class. All right, that's it for this class. Let me know if you have any questions. Thank you.